Hello? Hello? You can hear me, right? Alright. So, today is the third day of my study session, studying for the Physics Cambridge A2 levels before I finally have to take it. So, there's actually 4 days left until the. So today is the third day of my study session. Yeah. So there's actually 4 days left to my physics P4 paper. And yeah, so an update on yesterday. I didn't really get to finish the second paper yesterday. I didn't really get to finish it. So this morning I was just trying to finish it. Yeah, I did finish it. So now I'm just going to be marking the paper. Yeah. So for this one, I won't be listening to music because in case one day I actually take off on streaming, so I don't get DMCA copy strike or something. So I'm not gonna listen to music. I'm just gonna talk throughout this whole thing. Yeah, let's get marking. So for the first question, force per unit mass. Okay, that's correct. Pointing towards planet. Gravitational force perpendicular to velocity. Causes centripetal acceleration. Okay. T is 24 hours. 0.034. That's correct. Identification of two forces. Contact force. Yeah. So for question C2, they actually asked for like 2 forces, and I couldn't really think of the second force in order for it to have a circular motion. Yeah, so I thought it was resistive forces, but turns out it's contact force. Okay. 1 wrong. So that's 2 marks gone. So first one. 2A, thermal energy per unit mass. Okay. Energy per unit change in temperature. Oh, okay. So since Q equals Q over MC m delta theta, then it'll just be energy per unit mass and energy per unit change in temperature. Alright. Work done is 0. Increasing internal energy is E. Okay, that's correct. For the next one, work done, correct, negative E. And increasing internal energy, same as in B1. So that will be E. Thermal energy correct, so that it adds to work done to give increase in internal energy. So it's just W plus E. Yeah, okay. So to see more thermal energy needed, so specific heat capacity is greater. I didn't get to answer that question. I can't believe I'm missing out on like questions. I didn't see that question. Oh yeah, use the information in B to suggest with a reason how the average specific heat capacity of water between 8 to 16 compares with its average value. So just like we saw just now, since there's more thermal energy required, so specific heat capacity will be greater. Since you see like for the second one you need W plus E instead of just E, so yeah, more thermal energy is required. So that means that the Q equals to m delta theta, right? So C will have to be higher in order for Q to be higher. Okay, another one, pressure, volume, Boltzmann constant, that's correct. Number of particles, this number of molecules, and thermodynamic temperature. Okay, that's correct. B. Okay, this one's just derivation. You use PV is equal to NKT, and one of the other ones, it's P is equals to 1 over 3 NM over V root mean squared speed. So that's already in your formula sheet. Next one, U is equals to 480 meters per second. Yeah, I didn't get this one right. So yeah, for this one, I thought they asked for the root mean squared speed. Determine the root mean squared speed U. Root mean squared. Is that not it? Do I have to square it? Apparently I have to square it. Even though, yeah, it's kind of confusing. It says determine the root mean square speed u. Although we are already finding the root mean square of speed by, oh, I guess that, I mean, if you look at the unit, it already makes sense that it's not the square of u, it's just u, because if you square the u, it'll be m squared s squared. So yeah, that's my bad. But yeah, it's correct. The one I did was correct, but I just forgot to square it. So that's just one mark gone. Okay, next one. My graph was from here straight up, since pressure is directly proportional to the speed. So horizontal straight line. Yeah, I thought about that already. Yeah, because if you decrease the pressure, decrease the volume, as in you increase the pressure, even though the pressure increased, the particles will still have the same amount of energy since no thermal energy is supplied. So yeah, that was my initial answer, but then I doubted myself. I was like, if you increase the speed of the particles, the pressure will increase because they're hitting the walls with more force. So I thought, yeah, pressure increase, speed increase. But yeah, as long as you don't supply thermal energy in, the speed will still be the same, even though the pressure is increased. Okay. So for that one, yeah. Okay, for A1, determine the amplitude x naught and cm. So it's just from here to here, so that should be 8 cm. Yeah, let's just check here. Yep, 8 cm. Next one, 1.6 rads per second. So yeah, we did get that one. Use the angular frequency equals to 2 pi over t. Next one, E is equals to half m angular velocity square x naught square. Yeah, 0.29 joules. I got that correct. So the thing about this is they gave you 3 marks for this, which is like, it's quite simple. So it really threw me off. I was like, no, it's this simple for 3 marks. But yeah. So for those who don't know, the reason why it's half angular velocity square x squared gives you the total energy, it's because to find the, okay, so total energy is equals to kinetic energy plus potential energy. So when you have max kinetic energy, the total energy remains the same for the whole system unless there's resistive forces, but for this case there isn't. So if you have max kinetic energy, you would have 0 potential energy. So the formula for the kinetic energy would be half, oh sorry, we're using potential energy for this one, so half m angular velocity x squared, which is the maximum height. So if you have the maximum height, then if you're using the maximum height, your normal height over here will be 0, so that's why you're just using x naught squared. Yeah, it's something like that. I could have, maybe I've explained it wrong. Yeah. Okay, 4b. Wait, no, sorry. Yeah, okay, it's to find the kinetic energy. It's half m angular velocity squared x naught squared, which is the max amplitude, minus the current x squared, the one that you are using to find it. But since you're using the max height already, then your angular velocity squared here will be 0. So it'll be max minus 0, so you're just using x naught squared. Yeah. Okay, next one. 4b, dome-shaped curve starting and ending at ek equals to 0. Okay, yeah. Line intercepts h-axis at h equals to 2 and h equals to 18. Okay. Position of peak shown at 10. Okay. Maximum ek shown at 0.29. Alright, that's full marks. So for this one, you actually don't start over here. Don't start here because it doesn't reach here. The lowest would be 2 and highest would be 18, so it'll be 2, 18. And since when you're at the max height here, the ek will be 0, so that's why you would have zeros here, since when you are up high, it's full potential energy, 0 kinetic energy. It stops, but it has full potential energy. But when it reaches like the initial point, the middle, then it's traveling at the max speed. So when it's at the max speed, then it will have max kinetic energy. So that's why it's like a dome here. Yeah, okay. Let me just lock the door for a while. Okay, next one. 5A, define electric potential at a point. Work done per unit charge in moving positive charge from infinity to the point. Yep. Next one, the radius is 0.06. As long as you are in the radius, you wouldn't really get a change in the electric potential. So electric potential is constant, like a circle. As long as you are in like the radius, then in the circle you wouldn't get a change. But once the distance is like further away from the circle, then you would get a decrease in electric potential. Sorry, increase. Okay, 0.06, that's correct. Number 2, V is equals, okay, we'll use this formula, but the answer will be negative 5.7 times 10 to the power of negative 9. Okay, that's correct. 5C1, electric potential energy, you will use QQ. Okay, that's correct. Just need to remember these formulas. Okay, next one. Force is repulsive, so spheres move apart. Move in opposite directions. Force in direction of motion, so speed increases. Okay, I did not write this down. Potential energy converted to kinetic energy. I also did not write this down. Momentum is conserved, so velocities are always equal and opposite. Okay, I did write this down. Same speed, opposite direction, since momentum is conserved. Okay, so that's 1 mark. Force is repulsive, so spheres move apart. Okay. So I guess I get 2 marks from that only. So I need to write down. Force in direction of motion, so speed increases. Force in direction of motion, so speed increase. Okay, 6A. Potential difference across a resistor is equals to... Okay, we'll look at this first. The question. So it's asking you to explain the shape. Potential difference of resistor is equals to potential difference of capacitor. I did not write that down. No mark for that. Current in resistor is proportional to PD across it. I also did not write it down. Current causes capacitor to lose charge. Charge on capacitor proportional to PD, so PD decreases. I didn't write any of these though. Current causes capacitor to lose charge. Okay, so yeah, I saw this question. It's a bit like you get what it means, but you just really don't know how to answer it, you know. Yeah, maybe that's just me, but yeah, so I did get this one wrong. I just explained the graph actually. So first one is Q is proportional to potential difference. Oh sorry, not proportional, it's equals to. Wait, no, it's proportional. PD in resistance is equals to PD in capacitor, and charge proportional to PD, so PD decreases. Okay, B. Yeah, this one I'm really confused about like which one is it? This one, because you know, like it says 2 correct sets of readings. Even if you like get 2 correct sets of readings on like this one, because it says figure 6.2, like I took here and I got 5.28, it's 5.3, which is definitely not the time constant, which is like really weird. But although it's correct readings, so I would advise not using that. So the first one is a better one to use. So you're trying to find the the time at which it's like at the same time as the time constant. So that's the reason why you have -1 here, exponent -1. So you know that your Q naught is 0.9. So 0.9, you're trying to find the current, the amount of charge when it is in time constant. So you get this one, and from here you just look at the graph and you should get 5.5. Yeah. Okay, use figure 6.2 to show that the time constant of this. No, sorry. Use figure 6.2 and 6.3. Okay, capacitance in microfarad. You use C is equals to Q over V, since you have both Q and V. So I use the max values, which would be 120 micro. Okay, that's correct. Next one, T is equals to RC. Yes, you will use that one now. 46 kilo ohms. That's correct. 7A, force per unit current, force per unit length. Okay, that's correct. Current in wires perpendicular to field lines. Okay, now this one I got wrong. So I put the area. So when area is perpendicular, that's only for magnetic flux. But magnetic flux density, you would have to use the current. Okay, 7B1. Current in coil is perpendicular to magnetic field, so there's force on wire. Yeah. Okay, current in coil is perpendicular to magnetic field. Okay, so if it's flux density, then you just have to keep thinking of the current going through the wire. Yeah. Okay. So current is perpendicular to magnetic field. Force on wire is perpendicular to current and field, so it's a vertical force. Yeah. Using the left hand rule, that's why it's a vertical force. So based on the question, use the left hand rule, since it's like this, the fuel is going through here, horizontal, so you have to move it through like this, and then the current is going up, so the force is vertical, pointing up. So yeah, that's why it's vertical. And this one actually answers your next question, by the way. There's another question. So force is vertical, yeah, okay. MBIL equals to MG. Yeah. This one's my bad. I did not times it by the number of turns because I knew I had to put the number of turns in, but I don't know why I didn't. Because maybe it's because it didn't ask. It just said magnetic flux density. The flux density. So I just kept thinking like if you have the turns, it's the flux linkage. So it's really confusing. Determine what is now the. So basically, all questions you have to use all values given, no matter what. All the values here. They will be of use in your questions. Don't leave anything out, or otherwise one of your questions will be wrong. They don't provide redundant information. Determine what is now the reading on the Newton meter. Okay, so like just now, since it's pointing up, then you will know that the force is pushing it up, therefore you have a minus here, so it's the weight of this one. Okay, so it's 2.16 times 10 to the power of -3 times 9.81. Yeah, minus this one minus what I just said just now, and you would get 0.542. And yeah, your answer would be, because the force is upwards, magnetic force on balance and Newton meter are equal and opposite. Alright, direction of induced EMF such as to produce effects that opposes this is Lenz's law. Next one, yeah, this one is like really similar to all papers. They always show you this, and you just have to remember that this is the maximum of whatever is being asked here. It could be V, it could be I, yeah, and this one would be the angular frequency. So first one, X would be over here, which is 0.85, and t 0.04, so 2 pi 0.04 is 157. And you're supposed to round off to two significant figures, so 160. Okay, 2 cycles. Oh, sorry. Next one, they're asking you to draw a graph already. So here's how the graph goes. Since you have a decreasing gradient here, it's decreasing but very slowly. So you will need to first start at the top. Let's see. Okay, I'll point it out for you. Decrease. Okay, let's just say like this. It's decreasing the gradient, and you know that the potential difference is equals to the rate of change of magnetic flux. So as the current is changing, since the current is increasing here, you will have a change in magnetic flux. So that gives you the change in your voltage. But since the magnetic flux is like changing, and it's decreasing, the gradient here will be decreasing, and then it stops here, no change. So here will be 0 on your induced EMF graph. Then it increase, and here it'll be maximum. Over here it's the max, it's the steepest, and it'll decrease again, and it'll be 0 here, no change. So that's how your graph will go. It'll be like down, you reach 0 halfway through, whatever it's max, you reach 0, and then down when it was 0 here just now, so here you have your max, and then that's how it goes. So it's like a cosine curve, you know. Use laws of electromagnetic. Yeah, they say sinusoidal, but that's just the overall shape of it. 2 cycles of a sinusoidal curve with a period. Correct phase. V2 max min. The maximum and the minimum at 0, 0.02, and 0.04. Like I said, 0.02 will be your max, but over here minimum, and 0 will be a max. 0.04 will be a max, just like that. Okay, let's go to the next one. 9a. Energy of photon has a corresponding frequency. Oh, sorry, we haven't finished answering the questions. Proportional V2 is proportional to rate of change in magnetic flux. Yes, I did say that, but I didn't write that down. Oh my gosh. V2 is proportional to rate of change of magnetic flux. V2 has maximum magnitude when I1 to T curve is steepest. Okay, V2 is proportional to gradient. Wow. Use the laws of electromagnetic induction to explain the shape. Oh, you have to explain the shape, why it's like that. Yeah, my explanation's really off. My explanation was explaining like why there's the graph, but not why the graph is shaped that way. Okay, V2 has maximum when steep. V2 has minimum, 0, when no change in magnetic flux. Okay, next one. 9a1. Energy of photon has a corresponding frequency. Change in electron energy at level emits a single photon. So that's for question 9. Photon energy is equal to difference in energy levels. Discrete frequencies must have come from discrete energy gaps. Discrete energy changes imply discrete energy levels. Okay, this one I got nothing correct, so that's 3 marks gone again. Discrete energy levels as discrete energy changes, and photon energy is equals to difference in energy levels. Okay, next one. Okay, this one, transition, since you know that the photon energy is equals to the difference in energy levels, that's why you get this. Hc over lambda, energy of photon, is equals to the change in energy levels. So that's the reason why you have to times it by, divide it by 1.6 times 10 to the power of negative 19 as well, is because Hc over lambda will give you the joules. So in order to get it in EV, you will have to divide it by 1.6 times 10 to the power of negative 19. Your answer should be negative 1.51 EV. Next one. So I already did this whole thing already anyways, so while I'm marking it, I'm just showing you like why the answers are like that. Okay, state the name of the phenomenon that gives rise to a change in the wavelengths. So as the difference in wavelength, and it says rise again, so it's like increase in wavelength, you'll know that it's moving away already, so that will be the redshift. And what this shows about the motion of the galaxy is the galaxy is constantly expanding. Well, that's wrong, so it's moving away from the observer. Well, that's just basically explaining the redshift, but yeah. Okay, next one. We know that lambda is based on the formula V is equals to F lambda. We will get V is directly proportional to lambda. Yeah, so V is directly proportional to lambda. So wait, no, sorry. What was that again? Is it V equals to F lambda? Yeah, V equals to F lambda. So that's why you will get, for the velocity of like how far it's moving away from the Earth, you get how fast it's moving away, you'll get the difference of wavelengths is equals to the V. And from the electric spectrum, the spectrum, so from the emission spectrum here, you initially have 658, but then the observed spectrum, you have 686. This is the observed one. So 686 minus 658, that will give you how far it's moved away from the Earth already. And then that will be equals to the V, the speed that it's moving away. But using 658, you will get the normal speed, and over 3 times 10 to the power of 8. The normal wavelength is equals to the normal speed, 3 times 10 to the power of 8, or the speed that all particles move in the vacuum. Yeah, so that's how you get this formula. 1.3 times 10 to the power of 7. Okay, next one, V is equals to Hubble constant times D. That's just substituting everything, it's just algebra. Okay, 10a, introducing of tracer into the body. Okay, I did get that right. Containing a beta positron plus. That's a positron, by the way, beta plus. Introduce tracer, introduce positrons are in tracer. Okay, yeah, that should be alright. Okay, next one. Positron interacts with electron. Okay, annihilation occurs, mass of particles converted to gamma photons. Okay, and for this one, so since you already have here that the whole mass of interaction of positron and electron gives you the energy of gamma photons, so that's why you get E equals mc squared is equals to hc over lambda. So that will give you E equals m squared is equals to hc over lambda. So you will first find E equals mc squared, which would give you 2 times the rest mass of electrons, since you have 2 positron and an electron, times the 3 times 10 to the power of 8, the speed of light, times square. That will give you energy, which is equals to hc over lambda. So since there's 2 particles, you will need 2 Planck's constants as well. So 2 times 6.63 times 10 to the power of negative 34. So you move this here, move the E over, it will be hc over the energy that we calculated just now. So that's how you get this one. Yeah, so I guess that's it. That's it for this paper, and we'll move on to the next paper. This one I'm actually going to do now. Let's do 4.1. I have 1 paper left. I need to find more paper. or I need to be like very wise about the space I'm using. Okay, we'll start with 9702.41/n/22. So for today, I might just do one paper only, because 2 papers per day, it does get quite like mentally exhausting on you. It's a lot of papers. Oh yeah, I never really checked. How much time do you get to complete one paper? 2 hours, yeah. It's a really long paper, yeah. I mean, of course not compared to uni stuff, the universities, but like you get so much, it's very long for universities, but we're in A-levels, so speak A-level language for now. Okay, state the equation for the gravitational force F between 2 point masses M1 and M2 that are separated by a distance r. State the meaning of any other symbols they use. So this is just gravitational force, G F is equals to G mm over r squared. It's force, by the way, so it's r squared, not negative G mm over r. That's potential energy. So from here we get the only other constant we use is gravitational constant. That should give you your 2 marks. Okay, next one. B. A satellite is in circular orbit of radius r around planet M. Show that period t of the orbit is given by t squared equals to kr cubed, where k is a constant that depends on the value of m. Okay, so for this one, we actually have to do the gravitational force is equals to the centripetal force. So yeah, that's the pattern of the papers. Is like the first question is always something about gravitational force. Okay, don't know how you're gonna use that information, but use it as you may. Angular velocity square r. So we have gmm over r squared is equals to m angular velocity square r. So from here you can cross out the m. So you just have the gravitational field strength is equals to centripetal acceleration. So from here you move the r squared over, you get r cubed, gm equals to angular velocity square r cubed. See, it's now looking more and more like that equation. So next one, you would open the angular velocity square, square it, you'll be 2 pi over t squared. So it's gm equals to square of 2 pi over t r cubed. That will give you gm is equals to 4 pi squared over t squared r cubed. Now move the t over to the other side, so you have t squared, but you move the gm to the other side as well, equals to 4 pi squared over gm r cubed. So yeah, k would be 4 pi squared over gm, and which means that k is dependent on m already. That's it. Because you have to write it down, of course. Don't just leave it at t squared equals to 4 pi squared over gm r cubed. You have to just substitute it and leave it as t squared equals to k r cubed. Okay, next one. C. A satellite is in a circular orbit around the Earth with a period of 24 hours. The mass of the Earth is 6 times 10 to the power of 24. Calculate the radius of the orbit. Okay, for this one, firstly, you use this to calculate the, what do we do? Angular velocity. So angular frequency is equals to 2 pi over 24 times 3600, which is equals to 2 pi over 24 times 3600. You get 7.3 times 10 to the power of negative 5. So from here, you can actually, since you know the, what's it called? Wait, no, we can't just do that. The mass of the Earth is 6 times 10 to the power of 24. Gm. Oh yeah, you know the gravitational field strength is 9.81 already, so you can do. Oh, my bad. Yeah, we didn't have to find the angular velocity just now. We could have just found the field, used the field strength to calculate the radius. So gm over r squared is equals to 9.81. r square. R is equals to square root of 6.67 times 10 to the power of negative 11 times 6 times 10 to the power of 24 over 9.81. You square root the whole thing, so your R would give you square root of 9.97 times 10 to the power of 6.67 times 10 to the power of negative 11 times 6 times 10 to the power of 24, 9.81. That gives you 6.4 times 10 to the power of 1, 2, 3, 4, 5, 6. 6 meters. Okay, next one. Okay, I must have messed up somewhere. I don't think that's correct. Because, like I said, you can't just leave. Oh yeah. Dude, there's a reason why we calculate this. We get this formula, so you have to use this as well. Yeah, that was my mistake. Although I doubt it's actually wrong. I think it's still 6.4 times 10 to the power of 6, but maybe I'm wrong. Okay, 24 hours, 24 times 3600 square. Sorry, why did I square root it? Square, since t squared is equals to k, which is 4 pi square over 6.67 times 10 to the power of negative 11 times, what's that again? 6 times 10 to the power of 24, okay, times r cubed. So r is equals to cube root of 24 times 3600 squared over 4 pi square over 6.67 times 10 to the power of negative 11 times 6 times 10 to the power of 24. Okay, so cube root 24 times 3600 square over 4 pi square over 6.67 times 10 to the power of negative 11 times 6 times 10 to the power of 24. That should give you an answer. Okay, so it's not what I got just now. It's 4.2 times 10 to the power of 1, 2, 3, 4, 5, 6, 7 meter. Okay, so this one's a bit of an easy question, but you just have to not be careless. My mind feels like stone right now. It feels so stiff. Like you can, like brain cramps. Is that even a thing? Do you have brain cramps? I've never really got like any cramps in general. Like I never got any cramps before. Maybe if brain cramps is a thing, if brain cramps are a thing, then this would be my first cramp. Okay, 2 other conditions that must be met for the orbit to be geostationary. For those who don't know, it says 2 other. So there was one already stated, which is 24 hours. An orbit has to be in 24 hours for it to be in geostationary orbit on the Earth. And the second one would be, it has to rotate from west to east. And the second one, and the third one, the last one, has to orbit directly above the equator line. Equatorial line, equator line, equator, I think those work. Okay, number 2. 2a. State 2 other physical properties of materials apart from density of liquid that can be used for measuring temperatures. So the first one would be the fixed volume of gas. Volume of gas at fixed temperature. So how this works is, if a gas is, let's say if it's applied thermal energy to a gas, you could be, it will increase the internal energy. So you supply thermal energy, you get more, what's it called, velocity, and once you get more velocity, the volume of gas it'll hit it'll expand more, which causes the volume to increase. So you can use that to calculate how much it increase and take it to relate with temperature. Yeah, so that's how it works. And the last one would be just a very simple one, the EMF of a thermocouple. So you've learned about thermocouples in EF in O levels already. It's like really sensitive needle tips and all that to measure like really sensitive change in temperatures. But one more would be the resistivity of metals. Yeah, that's the more safer option to go with, resistivity of metals. So I'm gonna go with that. Since EMF of thermocouples, it's correct, but I'm a bit skeptical now. It's correct, yes, but I'm just, maybe the way I worded it is wrong. But yeah. Okay, the thermometer is initially at 23 degrees Celsius. As shown in figure 2.1, it is used to measure the temperature of an insulated beaker of water that is at 37.4 degrees Celsius. The bulb of the thermometer is inserted into the water, and water is stirred until the reading of the thermometer becomes steady. So yada yada yada, calculate to 3 significant figures the final steady temperature indicated by the thermometer in the water. Okay, so first thing you have to know is thermal energy supplied by the lost by the water is equals to thermal energy gained by the thermometer. So in the end, they'll reach thermal equilibrium. So first thing you have to do, mc delta theta is equals to mc delta theta, since mc delta theta is the thermal energy supplied or lost. So let's say the first one is loss, since the energy lost is equals to energy gain. Energy cannot be destroyed, energy can only be converted or transferred. So that's where you get the ideology from. So first one, mass of water in the beaker is 18.7. So first thing, 18.7. Don't need to convert it to kilogram because the units cancel out already on the, based on the equation, they'll cancel out. 18.7 times the specific heat capacity of water, which is 4.18, and the change in temperature would be 37.4. So first thing you know is 37.4, you lose thermal energy, so it will be negative. It'll be a negative change. However, you don't really want a negative in your equation, so it'll just be the thermal equilibrium, which is the one we're trying to find. So you will just put, let's say let's just put 37.4, the larger one, minus T, the one that we get. So that's a change in temperature. And for the next one, you will put 6.94 times heat capacity 4.18, 0.140 mc delta theta would be 23. Since it's gain, thermometer gains energy, you have to put the final temperature minus the initial temperature, 23. So yeah, a rundown, 18.7 times 4.1. Okay, let me just write down. 18.7 times 4.18, and then times 37.4 minus T. Okay, so let's just times it by 37.4. You will get 2923.4. Oh wait, no, let's not do it like this first. We'll just move this 2 over. The 18.7 times 4.18 divided by 6.94 times 0.140 gives us 80.45. So from here we can just do 80.45 times 87.4. You get 3008.9 minus 80.45 t is equals to t minus 23. So from here, with the t over, you get 81.45 t is equals to 3008 plus 23. $3031.9, and then you divide it by 81.45. You get 37 degrees Celsius. So that's your answer. T is equals to 37 degrees Celsius. Okay, it's really simple. This is the most simple 4-mark question I've ever gotten. Okay, next one. Suggest one more change that could be made to the desired temperature that would enable it to give a more accurate measurement of temperature. So, for it to give an accurate measure of temperature, we would want the thermometer to be absorbing less temperature for it to reach thermal equilibrium. So it'll have to absorb less thermal energy, because we want it to not have such a big difference in the thermal change. So to do that, we can either lower the mass of mercury that's in the thermometer, or we could get another liquid in the thermometer with a lower specific heat capacity. This is because Q is equals to mc delta theta, right? So if you lower the mass, you would lower the temperature. If you lower the lower the thermal energy gain. If you lower the C, then you would lower the thermal energy gain. So you can't really lower the thermal change, because that's what you're trying to do. Okay, so I'll just put down lower mass of mercury. So the main thing about answering these questions is you have to really remember the formulas of everything, remember the formulas, understand how they work, find the finding the relationship between each component is a very, very big part in all this stuff. Okay, C1, explain why the thermometer in figure 2.1 does not provide a direct measurement of thermodynamic temperature. So it does not give like a direct measurement, because 0 degrees Celsius is not absolute zero. And yeah, because the thing about this is like thermodynamic measurement, it goes by Kelvin. So if you measure by degrees Celsius, it's not the direct measurement of the thermodynamic temperature. So the answer would be 0 degrees Celsius is not absolute zero. Yeah. But that sounds like a 1-mark answer, so yeah, we'll check on that later. Thermodynamic temperature may be determined by the behavior of a type of substance for which T is proportional to the product of type pressure and volume. Once you read that, you should already know what it is. It's ideal gas. Okay, next one. Number 3. State the defining equation for simple harmonic motion. Identify the meaning of each of the symbols used to represent. Okay, 3a, a is equals to negative angular velocity squared x. So where a is acceleration, x is displacement, and angular frequency is angular frequency. Okay, B. For B, we'll look at the first question. Determine the amplitude x naught of oscillation. So x naught just means the maximum amplitude, which will be, as you can see here, the max potential energy is 0.05. So you will have max potential energy at the max displacement, so it should be 0.12. Or if you want to read this, you will get zero speed when you are at the max height, because like let's say when you swing this, when it reaches the maximum here, let's say if you swing a pencil, if it reaches like the maximum height here, it would stop, zero speed, before going down again, and then like the forces acting on it will cause it to decelerate and it will stop again. And then once this is maximum, it will have zero speed. Okay. Show the angular velocity frequency of the oscillations is 1.7 radian per second. So you already have the maximum displacement. So here it says the angular frequency. So you would use V is equals to angular velocity x naught. Okay. So your answer would be, let's say it has maximum velocity here, 0.2. So 0.2 over 0.12 is equals to angular velocity. That gives you 1.67 equals to 1.67, and therefore 1.7 radians per second. Determine the mass of the object. So for this one, you will actually use the potential energy here. So it's the third part. So you have 0.05 potential energy at the max height. So 0.05 is equals to half m angular velocity square x naught square. So it will be equals to half, and we don't know what the m is, angular velocity square, which is 1.7 square times 0.12 squared. You move everything over, you get m is equals to 2 times 0.05 over 1.7 squared, 0.12 squared, which gives you 0.05 over 1.7 square times 0.12 square. So that gives you 2.4 kilos. Okay. Next one. C. Oscillations are now lightly damped. State what is damping. So damping is basically the loss of energy of oscillations due to resistive forces. That's it. Assume that damping does not change the angular frequency of the oscillations. On figure 3.2, sketch the variation x of v when amplitude of the oscillations is 0.06. Okay, so over here, since we know that the angular velocity does not change, as stated here, so here we calculate. If angular velocity does not change, we use v is equals to angular velocity x naught again. So amplitude of oscillation 0.06. So let's say 0.06, we will have to find v naught. We know that angular velocity is 1.7, so your maximum velocity will be 1.7 times 0.06. That will give you 0.102. So it will be over here, somewhere here, which is half of it. So since it's 0.012, you would Draw a graph. You know that your max speed is 0.012. How would the graph look actually? Okay, so it'll just be a smaller circle within the circle, you know? So it's like here. Yeah. Angular velocity does not change though. So you have 0.102, 0.06, and that's how your circle will look. Same circle, but smaller. Okay, next question. For A, state what is indicated by the direction of an electric field line. Let me read the question. Sketch the direction of the digital oscillation is 0.06. Okay, next one. State what is indicated by the direction of an electric field line. So, direction of an electric field line will be what's this again? It's like direction of force on a moving charge. Yeah, something like that. Direction of force on a moving charge. Okay, that should be it. Figure 4.1 shows a pair of parallel metal plates with a potential difference of 2400 volts between them. Draw 5 lines to represent an electric field line. So since it's a zero potential difference over here, you will have lines going down here. So you have electrons coming in here. So of course they will be going towards the neutral area. 1, 2, 3, 4, 5 down like that. $2,400 V, 0 V will be going down. So 1, 2, 3, 4, 5. So I've been doing this question for quite some time, a lot of these questions already. So it's 3 marks because you have like 1 mark for just drawing 1 line. 1 line is 1 mark. And then you showing that it points down is another mark. And you drawing the other 4 lines is another mark. It's a lot of marks. This is like 3 marks. Okay, calculate the strength of the electric field between the plates. So for this one, you would use E is equals to V over D. So the potential difference will be 2400 over the separation 4.6 times 10 to the power of negative 2. So let's say this one is a negative 200 or something like that. Or let's say it's positive 400. You will plus them together. That's the potential difference. Wait, no, sorry, you will minus them. That's because potential difference. The difference in potential. You understand that. So if it's negative here, you would minus it. Yeah. So you just minus it actually. So okay. 2400 4.6 times 10 to the power of negative 2 equals to 5.2 times 10 to the power of 4 newtons per coulomb. That should be correct. Okay, next one. A moving proton enters the region between the plates in the field. On figure 4.2, draw a line to show the path of the proton as it moves through and out of the region of the electric field. So for this one, C1, you will draw the proton entering. So as it enters, since it's a proton, positively charged, it will be moving away from the positive charge side of the region of electric field. So you'll have a deflection going down, slowly going down, and then once you exit the field, it's just a straight line down because it's going down already. So it like follows the path, so it just goes straight other than that after that. Okay, number 2. So a helium nucleus now enters a region of the electric field along the same initial path as the proton and traveling at the same initial speed. Then explain how the final speed of the helium nucleus compares with the final speed of the proton after leaving the region of the electric field. So the thing about proton is it's a 1-1. Protons are 1 neutron, 1 electron. Yeah, okay. So for it being 1 neutron, 1 electron, that means that the helium nucleus is twice the charge, but 4 times the mass. So as it is twice the charge and 4 times the mass, the path will actually be a bit the same, I think. It'll have the same path due to it having equal ratios. No, sorry. Twice the charge. It'll be going down more. It'll have a... How do I write that actually? Oh, sorry. It's asking for the speed, not the path. Okay, so it'll have a greater... Wait, no, sorry. Less speed when it exits the field, because more mass means less velocity due to the momentum formula. Okay. Hence, less speed. That should be it. Okay. Next one, 5 capacitor of capacitance 470 micro is connected to a electric field. Okay, calculate the charge on the capacitor at times t equals to 0. So the capacitor, we know it's 470 micro. Okay, so 5A 1 Q is equals to CV. The charge will be equals to 470 times 10 to the power of negative 6 times 24, just equals to 470 times 10 to the power of negative 6 times 24. You get 0.011 coulombs. Yeah, I do this a lot. I double take a lot to try and like make sure that I didn't make any careless mistakes, because I'm pretty known for like making careless mistakes. Okay, next one. Calculate the current I in YP at time t equals to 0. So at time t equals to 0, move to position Y. When it's just moved to position Y, you will still have full potential difference here. But yeah, you will still have potential difference here. So number 2, V is equals to IR. I is equals to V over R, which is equals to 24 over 5.6 times 10 to the power of 3. 5 times 6 times 10 to the power of 3. Since it's kilo ohms, 24 over 5.6 times 10 to the power of 3. You get 4.3 times 10 to the power of negative 3 amps. Okay, next one, calculate the time constant. Okay, this one's just, you just have to remember the formula. T is equals to RC, which is equals to 5.6 times 10 to the power of 3 times the capacitance, 470 times 10 to the power of negative 6, which is equals to 5.6 times 10 to the power of 3 times 470 times 10 to the power of negative 6. 2.6 seconds. Okay, next one. On figure 5.2, sketch a line to show the variation of T of the current I in YP as the capacitor discharges. So for this one, when the capacitor discharges, the stored current is decreasing. The stored charge is being discharged, so it's decreasing. So you know it's a negative gradient. So it just matters whether it's a straight line or a curved line. So you know that it will never decrease completely to zero, since the switch is constantly moving. So you have an asymptotic, I think that's how you call it, line that never reaches zero. So it is a negative gradient. You have T is equals to RC, R is equals to V over I, so T will be inversely proportional to I. So that means you get a curved line that the gradient just starts decreasing. The gradient of line is decreasing, not constant, since it will not reach zero. The current will not reach zero. Okay, next one. B1. Explain why there is an induced EMF across wire Q during the discharge of the capacitor. So, this one. Wire Q has induced EMF because as you pass current through wire P, a magnetic field is produced, which wire Q cuts. And when wire Q cuts the wire P, it has induced EMF on wire Q, which in turn produces eddy currents. That's why there's current. Oh, sorry, induced EMF. It just wants induced EMF. Okay, so I think how I write it is current pass through P, magnetic field produced, wire Q cuts field, hence induce EMF. Okay. On figures 5.3, sketch a line to suggest the variation with T of the voltmeter reading V. So I actually need more paper for this one. Just give me a second. More paper. Okay, this is 5B2. 5B2. So the graph would be okay, so capacitor discharges, you will have current going through here, a large current, so there's a large change in EMF. So in the beginning, you would have a huge spike here, large change in EMF, so it's a gradient increase. But then, as the current starts to get lower, you'll have like lower changes in induced EMF, so lower voltage, and it won't reach zero. So you'll have a bit of a straight line, but it's not straight. So yeah, so it's like a curved line, like up like this. Okay, next one. 6. We're on question 6. 6A. Thin slice of semiconductor, yada yada. Current I passes through the slice in the direction shown. Current is going in. A steady Hall voltage is developed between phase PQ, XW, and S. PQ, XW, and SRYZ. Identify the phases that are perpendicular to the magnetic field. So left-hand rule, Fleming's left-hand rule. If current going in, and that means the magnetic field will be pointing here, pointing horizontally. So that means the phases perpendicular will be PQRS and WXYZ. That's your answer. Wait, let me think first. Current going in, field is to the left. That would mean that the perpendicular would be oh, sorry. You have to look at this also. So the VH is developed in PQXW and SRYZ. So that means the force is this way. So it's like this. Current is going in through here. The force is pushing the particles to the horizontal. That's why there's a Hall voltage in PQXW and RYSZ. Hence, your Fleming left-hand rule will look like this, and therefore the magnetic field is going upwards. Therefore, the perpendicular would be PQRS and WXYZ. Okay, explain how a steady Hall voltage is developed between the faces PQXW and SRYZ. Okay, for this one, as your current is perpendicular to magnetic field, there's a force produced, and it is exerted pushing electrons to faces PQXW and SRYZ. Sorry, it's only pushing it to like one of the field. It's either PQXW or SRYZ. So faces, let's just say PQXW. Therefore, face becomes charged while the other face does not. Therefore, there is a potential difference, which is Hall voltage, and it will be safe to write down once a magnetic field is equal to the force, then Hall voltage is constant. Okay. So B. N will be equals to number of charge particles, oh sorry, number density. T would be equals to the thickness and Q will be equals to the charge of particles. Okay, number 2. Suggest with reference to the equation why the slice of material used in the Hall probe is thin. So again, so from this, sorry, from N just now, number of density is not of charged particles, it's just number density of particles. And number 2, suggest with a reason, reference why it must be thin. So as it's thinner, you will know that the volume is decreased because it's thinner, you know. So thinner means lower N value, therefore VH is higher as VH is inversely proportional to N, therefore easier to measure VH. Okay, next one, 7A. A sinusoidal alternating voltage has a root mean squared potential difference of 4.2 volt and a frequency of 50 kHz. By considering the peak voltage, show that the maximum power dissipated by the resistor is 46 milliwatts. So from here we can use P is equals to V squared over R. Since we know that the root mean squared is 4.2, so the maximum voltage will be 4.2 times root 2 over, sorry, we have to square it, over 760 ohms, which will give you 4.2 root 2 squared over 760. That gives you 0.046 watts, which when you move 3 units to the right, 1, 2, 3, that gives you 46 milliwatts. And therefore it is shown. So for number 2, on figure 7.1, draw a smooth curve to show that how the power P dissipated in the resistor varies with time t. Whew. So since the frequency is 50 kilohertz, the period will be equals to 1 over 50k, which is equals to 2 times 10 to the power of negative 5. So that's the period, which is also 20 microseconds. So therefore, the power dissipated, since you know the max power dissipated is 46, you would count from here, just around here somewhere. So I'll just write down you have to count it properly, of course, when you do it in an exam, but now we'll just estimate. So 20, 10, 30, 40. Okay, so it's 2 microseconds per cycle. So the alternating voltage goes back to its normal voltage at 20. So in the beginning you would have like the max voltage, so you would start here, you will go down here. Since it's alternating, you would have a positive voltage and negative voltage, but since power is a scalar, you don't really have a negative power, you only have negative energy. So you would go from 46 down here, middle, 5 microseconds, and then at 10, halfway through the cycle, the alternating voltage reaches the negative value of the voltage. So you go all the way up, same power dissipated, all the way down, zero power, all the way up. So that's how it goes. So from max, down, up, down, up, down, up, down, up. You end at 40 with max. Okay, use your line in A2 to explain why the mean power dissipated in resistor is 23 milliwatts. So the mean power, you will just have to find 46 divided by 2. That's your mean. But it's actually, you have to find like 23. 23 is actually where they're symmetrical. You know, the line 23, that's where it becomes symmetrical. As 23 milliwatts is is line of symmetry. You can't just say it's 46 divided by 223. You have to say like it's symmetrical, it's at the middle. Okay, next one, the alternating voltage in A is now applied to a pure piezoelectric crystal in air explain what happens to the air surrounding a crystal. As alternating voltage is applied to piezoelectric crystal, the crystal starts to produce ultrasound waves actually. So it starts to vibrate, creating the waves. So that means the air around the crystal starts to vibrate. Yep, so B1 as PD applied, crystal vibrates. Hence, surrounding air vibrates. Okay, number 2. Explain the effect of the surrounding air in B1 on the second crystal. So they start vibrating. So the air around the first piezoelectric crystal touches the second piezoelectric crystal and causes the second crystal vibrates, producing induced EMF. So yeah, you get induced EMF on your second crystal. Done. Next one, 8A. State what is meant by the work function energy of a metal. So it's the amount of energy required for one electron to be emitted from the metal. So it's one photon energy actually, the amount of photon energy required to move an electron with zero kinetic energy. So we'll just put down amount of photon energy required to move an electron with zero kinetic energy. Okay, next one, 8B1. Ultraviolet radiation of frequency 1.36 times 10 to the power of 15 Hertz is incident in a vacuum on a metal surface. The power of radiation incident on the surface is 8.36 milliwatts. Photoelectrons are emitted with a maximum kinetic energy of 3.09 times 10 to the power of negative 19. Determine the number of photons incident on the surface per unit time. So for this one, we know that power is equals to work done over time, and we know that E is equals to HF. So we get HF over time. So what we're trying to get actually is just the 1 over T because it's per unit time. So we move the HF over, so we have P over HF is equals to 1 over T. That's what we're trying to find, which is equals to 8.36 milliwatts times 10 to the power of negative 3 over HF 6.63 times 10 to the power of negative 34 times the frequency 1.36 times 10 to the power of 15. That should give you your emitted per unit time. It's really tiring doing this much physics. 10 to the power of negative 3 over 6.63 times 10 to the power of negative 34 times 1.36 times 10 to the power of 15. You get 9.3 times 10 to the power of 15 per unit time. Okay, next one, calculate the work function energy of the metal. Work function of the metal. So from this one, the equation is HF is equals to work function plus KE, kinetic energy. So you know the kinetic energy is 3.09 times 10 to the power of negative 9. So you put HF first, 6.63 times 10 to the power of negative 34 times 1.36 times 10 to the power of 15 over 3.09 times 10 to the power of negative 19 is equals to, sorry, not time, sorry, not divide, my bad, it's minus 3.09 times 10 to the power of negative 19 equals to work function, which gives you 6.63 times 10 to the power of negative 34 times 1.36 times 10 to the power of 15 minus 3.09 times 10 to the power of negative 19. You get the answer again, 5.9 times 10 to the power of negative 19. That's your work function. Don't forget to put the joules. Okay, the frequency of the radiation incident on the surface in B is increased while the power remains constant. So when you increase the frequency, since V is equals to F lambda, V is directly proportional to the frequency. So increasing the frequency will increase the speed of the electrons. Lambda will remain the same, of course. So that means for C1, as frequency increase, electrons move faster. Hence, kinetic energy will increase. Now for the second part, rate of emissions of electrons, since the power remains constant, intensity remains constant as well, I over A. So since the intensity remains constant, you won't get as much, you won't get an increased amount of electrons emitted. You won't get increased amount, you won't get decreased amount. So rate of emission remains constant as no change in power, and power is directly proportional to intensity. Okay. State what's meant by the luminosity of the star. Power of emitted EM radiation. Is it EM waves or EM radiation? I think it's radiation. EM radiation of star. I think it's EM waves. I'm gonna put EM waves. A star in the constellation Canis Major is a distance of 8.14 times 10 to the power 16 from the Earth and has a luminosity of... Oh, it's really tight. My brain is actually like really hard. It's really stiff now. B1. I feel like I'm overclocking my brain. So calculate the radiant flux intensity of the radiation from the star observed from the Earth. So radiant flux intensity sorry, you can't really find it, but radiant flux intensity is equals to F is equals to L luminosity 4 pi d square. L is equals to F is equals to L over 4 pi d square. Therefore, your L is 9.86 times 10 to the power 27 over 4 pi. Separation is 8.14 times 10 to the power 16. You would get 9.86 times 10 to the power of 27. The answer is divided by 4 pi times 8.14 times 10 to the power of 16 squared. And that gives you 1.2 times 10 to the power of negative 7. And the unit would be, since you have L on top, L is luminosity is just I over A, which would be the power, and you have meter square below, so it will just be watt per meter square. Okay, next one, determine the radius of the star. So for this one, you have to use the relation formula. So you have here L is, sorry, where is it? You have here Stefan-Boltzmann law. L is equals to 4 pi Stefan-Boltzmann constant r squared T4, and L, you know, it's equals to L over 4 pi d squared. So that means that T4 is inversely proportional to r squared. So that would mean that, sorry, where am I? This is not the correct question. This is the past paper I was doing. Okay. Move down. You would get. I'm really tired. Determine the radius of the star. You would have r squared over surface temperature is 9830. So since it's inversely proportional, r squared is inversely proportional to T4. It's T4, right? You'll get the r squared, which is the distance between the Earth Ah, 16 squared, sorry, 10 to the power of 16 squared is equals to 9830 Kelvin, the surface temperature of the star. And you have the, oh wait, well, we can't do that because we don't have the surface temperature of the star from Earth. How would we do this? Well, I guess we could say L is. No, you can't say that. No, for this one, don't use any relation. Just straight away use the Stefan-Boltzmann law. So you already found the radiant flux intensity of the star. So you should, no, sorry, you have the luminosity. So it's 9.86 times 10 to the power of 27 is equals to 4 pi Stefan-Boltzmann law, 5.67 times 10 to the power of negative 8 r squared, and T4, which is the surface temperature of the star. So you're trying to find the radius, so your r squared, T4, surface temperature, 9830. Yep, so from here you find r squared. R would be equals to 9.86 times 10 to the power of 27 over 4 pi 5.67 times 10 to the power of negative 8 times 9,830 square root. R will be equals to root of 9.86 times 10 to the power of 27 over 4 pi 5.67 times 10 to the power of negative 8 times 9830. So your answer, the radius should be 3.75 times 10 to the power of 13. That should be your answer. Oh, sorry, my bad. I forgot to put the temperature to the power of 4. Yeah, I was wondering why it's so big. 1, 2, 3, 4, 5, 6, 7. So it's just 3.8 times 10 to the power of 7. Let me just confirm the Stefan-Boltzmann constant. 5.67 times 10 to the power of negative 8. Okay, that's correct. Okay, let's move on to the... Oh, sorry, we have one more question. C. This is 9C. Explain how the surface temperature of a distant star may be determined from the wavelength spectrum. So this is where you use Wien's displacement law. Wien's displacement law, where what's that? Lambda is inversely proportional to temperature. Is that it? Or is it T is inversely proportional to lambda? It's called displacement law, so I'm guessing it's lambda is... I actually forgot, but yeah, it should be lambda is inversely proportional to 1 over T. Let's just make sure. Yeah, it's correct. Okay. Wien's displacement law. So we can use this to determine the observed explain how the surface temperature of a distant star may be determined. Okay, the observed wavelength from distant star and compare with known wavelength and temperature, and from there we use Wien's displacement law. Yeah. Okay, next one, the last question. 10A. What is meant by random? Random means that it is unknown which nucleus will decay next and when it will decay. Okay, number 2, spontaneous. So spontaneous means it is independent of external, and don't put it, just put decay. It is independent of external / environmental factors. Okay, B1. State how figure 10.1 demonstrates that the radioactive decay is random. So we can say line is not straight. That's the answer. The line is not straight. I think that's just the answer. Next one, state on figure 10.1, draw a straight line of best fit. You just draw a straight line, that's it. Number 3, show that the decay constant of carbon 15 is given by the magnitude of the gradient of your line in V2. So here we actually do the decay constant. It would be what's that formula again? It's like something about the mass is equals to the mass naught E negative lambda T. Yeah, that's it. Okay, so from here you have mass over mass is equals to E negative lambda T. You will move the E over, you have ln m over m naught. That gives you your y already, since m naught is still G. And from there you would have over T is equals to negative lambda. So therefore it's shown. That's it. So it's only one mark. Next one, use your line in B2 to determine lambda. This one you have to use a line, but I don't have my line yet, so basically you just have to take one value from your line and all that and calculate. I'm just gonna skip that. It's quite simple. It's just finding the gradient. You find y1 minus y2 over x1 minus x2. Okay, I'll just do it. You have 0 and negative 5. Since the fluctuations are very small, I think even if I use this line, it should be around the same value. And let's say 10 is here, which is around 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 6.5. Oh, sorry, it's 5.5. 5.5. Wait, is it though? I'm actually confused now. Sorry, half. 1, 2, 3, 4. Yeah, 5.5. So 5.5. The difference is 1, so 0.01. No, sorry, 0.1 each division times 5.5. You get 0.55, so it's 7.55. So y1 would be negative 7.55 minus negative, what's this? 4.8. 4.8 plus 4. Minus 4.8. You get x1, which is from what I said just now, 10 seconds, minus x2, which will give you negative 7.55 plus 4.8. Answer divided by 10 should give you 0.275. The unit will be per second, by the way, because that's the decay constant. Okay, number 5. Use your answer in B4 to calculate the half-life of carbon-15. So half-life. So we have decay constant. Decay constant is just equals to 0.693 over half-life. So your half-life will be equals to 0.693 over decay constant. But the other one would be time constant is equals to half-life over 0.693, which is ln 2. Yeah, don't get that confused up, yeah? Don't confuse that. 0.275, you get half-life of 2.52 seconds. Let's just verify that. 2.52 seconds. Yeah, probably not. That's the mass. Okay, sorry, we can't verify that. So C Next, they explain how the mass of the products of decay must compare with the mass of the carbon-15 nucleus. This one I'm not really that sure. So okay, as carbon-15 is decayed, mass has to be fully converted. Hence, products has higher mass. Okay, that's it. Let's look at the mark scheme. Let's go all the way down. Less than. Okay, so energy is released. Energy comes from fall in mass. Oh yeah, so the fall in mass is equals to the product, so it must be less than. Yeah. Alright, so I got it wrong in this one. Energy released E equals to mc squared, therefore less than carbon 15. Okay, 2.5 seconds. We got that correct. 2.8, 2.75. Yeah, we got that correct too, without drawing a best fit line. But yeah, you need to draw the best fit line in the exam. M naught is equals to exp negative lambda t. Okay, that's correct. But for this one, they loaned everything first, and then they separated it after. So probably this is the correct way to do it, because from the way I did it, you wouldn't be getting a unit of G because it's divided, so it's a ratio. So you wouldn't be getting a unit with it. So probably the way I did it was wrong, but it's almost similar. Line fluctuates, trend is a straight line. Wait. I guess the line fluctuates. Okay. Means that it's random. So not affected by external environmental factors. Okay. Cannot predict when a particular nucleus will decay. Unknown which nucleus will decay. Okay. Cannot predict which nucleus will decay next. Yep. Okay, I did write that down. Okay. Next one. 9C. When's displacement law is used. Okay. Wavelength of peak intensity determined. I didn't really write peak intensity, so I don't think I'll be getting a mark from that. Wavelength of peak intensity from object of known temperature determined. Okay, compare the wavelength of wavelength and temperature. So I have to include peak intensity. Okay. Next paper, 9B2. Radius is 1.22 times 10 to the power of 9, so I got that one wrong. How did I get that one wrong? 9.86 times 10 to the power of 27 divided by 4 pi, 5.67 times 10 to the power of negative 8. Divided by 98304. Oh, it's probably because I know I put 27 in my question, but probably in the calculator I put I put 17 instead. Probably that's the error. Let me check. Probably I entered something wrong. Yeah, but from what I've written down, it's actually correct. But it's just so you can. I hope you can see it. From what I've written down, it's actually correct. But I think what I put in the calculator is wrong. Okay. B1, 1.2 times 10 to the power negative 7, that's correct. Power of radiation emitted. So it's radiation, not waves. Number 2, rate of emission remains constant as no change in power, and power is, so first one, greater photon energy, so it's lower rate of emission, my bad, because the frequency is increased in greater photon energy and same power. Frequency is increased, so you have greater photon energy, so you will have the same power. Okay, since the work function remains constant, so you will need to reduce the amount of photons. Okay, that's wrong. You have to use the formula HF is equals to work function plus KE. Okay, next one. My bad. Rate of photon energy, same work function. So kinetic energy is increased. 5.93 times 10 power negative 19. Okay. 9.27 times 10 power 15. Alright. Photon energy to remove electron. Yeah, I did write photon energy. To move an electron with 0 kinetic energy. Alright. Next one. Air makes crystal vibrate, which causes EMF to be generated across second crystal. Alright. Frequency is in ultrasound range, so I did not write that. Vibrations of crystal causes air to vibrate. Okay. Crystal to vibrate. Okay. Line symmetrical about 23. Okay. 4 cycles of repeating pattern. Correct shape sinusoidal. Peak at 46. 4 cycles of repeating pattern shows P equals to 0 at 0, 10. I got this one wrong. So it's completely wrong for me. My peak is correct, so I do get 1 mark from that. It's the correct shape, so I do get another mark, but my points where it's 0 is wrong. Yeah, that's wrong. Next one, 46 milliwatts. Okay, I did get that one. 5.9 volts. Okay, next one. PQRS WXYZ. Okay, force on charge carriers perpendicular to both magnetic field and current. Charge carriers are deflected to one side and electric field is set up. One side. Okay. Study VH when electric and magnetic forces on charge carriers are equal. Okay. N is the number density of charge carriers. Okay. T is the distance of PW, which is basically the thickness, but yeah, I guess that's too vague. Charge on each carrier. Okay. Next one, sketch shows line with a negative gradient throughout. I have B2, gosh, so I got that one wrong. Yeah, makes sense. Okay. B1, current wire gives rise to a magnetic field. Okay, as current in P changes, wire Q cuts magnetic flux. Okay, hence induced EMF. Okay. A4, line with negative gradient throughout passing through 0 I naught. Okay. Exponential decay curve asymptotic to t-axis. Okay, I did say that. Okay. 2.6 time constant. That's correct. Number 2, 4.3 times that. Okay. 0.11, 0.11. Okay, correct. Final speed is lower for helium. Okay, less speed. Okay. Velocity parallel to plate, same, and acceleration perpendicular to plate, smaller. Double the charge with 4 times the mass, so I get 2 marks only. Velocity parallel to plates, same, and acceleration perpendicular to plates, smaller. Okay. E is equals to V over D. 5.2 times 10 to the power of 4. Which I did get that. Okay. C1. One straight line perpendicular to plates. I know that's drawing the lines. C1 smooth curve in regional field and straight line outside field. Direction of deflection shown as downwards. Okay, that's correct. Direction of force on a positive charge. Okay. Number 3. 2.4 kilos. Do I have 2.4 kilos? No, I don't. Why? Why is it not 2.4 kilos? Closed loop surrounding the origin with a maximum of x hat passing through V0. Okay, so my circle is correct. Loss of total energy in system due to resistive forces. Alright. Why is it 2.5? I did get it correct. Half mv squared. I use half m squared. Okay, I use this one. 1.67. Oh, he just rounded it off to a more precise one. He didn't leave it as this one. I did say to do that last time in the last stream, but I myself didn't do that. Okay. X0 0.12, correct. Is okay, the formula is correct. Acceleration, displacement for equilibrium position, and angular frequency, that's correct. Last 2 questions. Ideal gas, correct. 0 degrees Celsius is not absolute 0. Okay, that's correct. Depends on properties of a real substance. Okay, I did not include that. Depends on properties of real substance. Okay. Use a liquid, use a smaller mass of mercury, so I did use that. Okay, 37.2. Is that my answer? That is my answer. Okay. Resistance of metal, EMF of the thermocouple. Okay, and volume of gas at constant pressure. Okay. Radius is 4.2 times 10 to the power 7. That's correct. Rotate must be above equator, orbit directly above the equator. Direction must be from west to east. Okay. Completion 4 pi squared over gm is your k. That's correct. And F is equals gmm over r squared. G is the gravitational constant. Okay, that's all. Okay, so I guess that's all for this stream. I completed 1 paper and I am really tired right now, so I'm probably going to eat dinner and go to sleep already. So I hope one day more people will watch my stream actually, because I'm literally talking to no one right now. But yeah, maybe one day I'll actually do well on YouTube. I'm not looking to pursue YouTube as a career for now, but if it looks good, of course I'll pursue it as a career. So yeah, I guess I'll see you guys when I see you guys.
Alright, bye bye.